Welcome along to episode 3 of this devblog series. I have decided that this session will have captions, so that hearing impaired folks in our developer community can follow along. This is one of the reasons why I am using text-to-speech. Today, we will be looking at a small file helper class called CVFile. It effectively has just two functions. The first function, fileLastWriteTime, gets the time when a file was last written to, and returns the result as a straight number, which is held by a uint64. The second function is a directory walker or grep, that we will come to later. As you can see, the function parameters are pushed onto the stack. This means that we can use this class from different threads, as long as each thread uses this class within its own memory space. This is why these functions are not static, and we use the stack to our advantage. Let's take a look at the first function. In a later episode where we compile shader files, using Microsoft's latest offering DXC or DirectX shader compiler, then, we will want to compile shaders, but only if they need to be rebuilt. For that purpose, being able to compare time date stamps easily between the source and object files is a must. Hence this function. Now you might be thinking that this is going to be easy. However, there is a caveat. Let's take a look at the Win32 file attribute data. Notice that the file time is actually made up of 2D words. We cannot simply cast that to a uint64. Because sometimes it will work and sometimes it won't, especially if you are building for Windows using different architectures. We need to translate this value, using a structure created for this purpose. It is this large integer. Let's check this out. As a side note, why is there a dummy union in there? Well, it is to support compilers that don't like anonymous unions. So, this large integer is a union that contains 2D words, which may also occupy the same space of a long or uint64. I say may, because it really depends on the architecture of the machine that you are building for. This becomes a problem as we need to convert those D words to a 64-bit unsigned integer. Why? The rules for determining alignment structures are platform-specific. For example, _int64, log integer, etc., must be aligned on a 4-byte boundary for some x86 platforms. But for other platforms, using say an Itanium, they must be aligned on an 8-byte boundary. If the alignment cannot be guaranteed, then we need to handle the conversion ourselves, as taking the quad part value won't produce consistent results. That could be a nasty bug to find later on down the road. If we are building for x64, then alignment is guaranteed to be on a 16-byte boundary. It is only when building for x86 that we need to be more careful. The question is, how can we programmatically test for an x86 or x64 build under Windows? We could use hash defines and build for specific platforms, but that can make the code much harder to maintain. Determining the platform on the fly could prove to be advantageous. One way to test this is to discover if WoW64 is being used as a bridge between an x86 build and 64-bit Windows. Windows does actually provide a mechanism to discover if WoW64 is running, hence this call to _ is 64-bit Windows. It simply returns a yes/no answer. There are a lot of comments here for a simple single call. But if I came to this say in a couple of years' time, I probably would not remember how it works. So these comments are, for me, valuable. Let's get into the detail. My system on this PC is running 64-bit Windows. If we are building for 32-bit Windows, then, Under the hood, Windows will be using WoW64. Microsoft quotes on WoW64 to seamlessly convert all the 32-bit calls to 64-bit before processing them. Thus, if we can test if WoW64 is running, and if it is, our code base must be 32-bit. So now we have a method to see whether we have a guaranteed alignment for the large integer and can use the quad part value. The call to is WoW64 process 2 when called will fill out the two U shorts that we pass in. All we are interested in is whether we have 0 or non-zero values, as my function is simply returning a true or false. As you will know, the line of code is processed from left to right. So after the call is made, the result from is WoW process 64 will be either 0 for a fail or non-zero for a successful call, and this result is ANDed with the variable US process machine, which can also be 0 or non-zero. So, what are the permutations for this line of code? The first case. If the call fails, US process machine will be 0, so the call result, ANDed with 0, equates to false. This is then inverted and the return value is true. So it probably is a 64-bit Windows build. Ideally more checking should be performed, but I only need to know if WoW64 is running or not. The second case. If the call was successful, then WoW64 is running. US process machine will be filled out with the type of code that has been compiled. In my situation, it is Intel 386. You could of course get other values depending on build configuration, for example ARM. So now we have a non-zero successful call and a non-zero US process machine. The return result will be true as WoW64 is active. That is then inverted saying that our build must be for x86, not a 64-bit Windows build. The third case. If the call was successful, but US process machine came back as 0, or image file unknown, then this will equate to a false. This case could be tested in a real-world situation, but in reality, it would take a very strange build for this to occur. Perhaps it could be a quality control question? But here, I am simply assuming that WoW64 is not running. This result is then inverted, and it is a 64-bit build. That's it, so we get true if it is running Windows 64, or false if it is not. A further optimization is at the top of this function call. If _win64 is defined, then it must be a 64-bit build. In which case we simply return true. Now we can decide how to convert those 2D words into a uint64. If it's a 64-bit build we can simply take the quad part. Otherwise, the safe bet is to build the uint64 like so. Setting the high part and shifting it left by 32 bits, then ORing in the low part. Finally, the uint64 is returned, giving us the number of 100 nanosecond chunks, since January 1, 1601. A pretty large number. All we have to do is compare the numbers and we have a mechanism that tells us whether we need to rebuild a shader file. Let's move on to the directory walker. Thanks to the latest innovations in the STD libraries, we can now use the STD directory iterator. The two entry points set up the path where we need to start traversing, and the file extension we are interested in. When these functions return, all the files that we came across that had the matching extension will be stored in a list of strings. This can then be used by our shader compiler code to provide fully qualified file names that DXC will use for compilation. DXC will ask us to provide details for include files too, So having a list of all the shader files will make life much easier. Recursive functions can be hard to get your head around sometimes. I personally like using them, but I know that for some folks, they can be a real headache. This is the main loop inside the function, so, speaking as in pseudocode. For each entry in the directory, if it is a directory, recurse and start again. Otherwise, if it is a regular file, check the extension, and if it matches what we are looking for, then store the fully qualified file name in the list. And then continue with the next entry. When we have checked all entries in that directory, drop out and return to carry on with the next directory, until all entries have been checked. It really is that simple. You have to be aware that if the directory tree is very deep, then a recursive function like this can run out of stack space. Your process will not be very happy, and will fall over. So you need to be aware of the maximum depth in all recursive functions. You could of course feed in an integer for depth count, and stop going too far, but for my directories, they're quite shallow. So there is no need for me to worry. Notice the call to Unicode to CV string. This is because on a MBCS build, the directory entries are still coming back as Unicode. So the call is used to crunch the strings back to the narrow versions. Moving on to the tests. The file time date stamps are just being compared to discover if one file is newer or older than the others, a very basic test. The exgrep test is walking a known directory tree, with known files, to place in the vector list. We are expecting 3 files to be returned, each having an extension called txt, which was what we... And the results? MBCS x86? All good. MBCS x64? All good. Unicode x86? Yes, that works fine. Unicode x64? Perfect. Oh, happy days. I hope you have made it this far. If you have, thank you so much. I wrote a program to provide the captioning, so future videos will be much easier to produce. I may even make a video on it. Let me know if you are interested. Finally, that concludes this episode. Thanks for watching. Catch you later.